Hey guys, and welcome back to this class, Convolutional Neural Networks, Deep Learning in Python, Part 3. In this lecture, I'm going to give you guys a crash course on convolution. If you really want to dig deep on this topic, you'll want to take a course on signal processing or linear systems. So what is convolution? Think of your favorite audio effect. Let's say we're talking about the echo effect. An echo is simply the same sound bouncing back at you in the future, but with less volume. We'll see how we can do this mathematically on the next slide. All effects can be thought of as filters, like the one I've shown here, and they are often drawn in block diagrams. In machine learning and statistics, these are sometimes called kernels. So let's look at visually how we would create an echo. I'm representing our audio signal by this triangle. Remember that we need to do two things. We want to hear this audio signal in the future, which is basically a shift to the right, and this audio signal should be lower in amplitude than the original. I've shown two of these in this figure. And the last operation is to sum them all together. Notice that the width of the signal stays the same, because it hasn't gotten longer or shorter, which would change the pitch. So how can we do this in math? Well, we can represent the amplitude changes by weights called W. And for this particular echo filter, we just want to make sure that each weight is less than the last. For any general filter, there wouldn't be this restriction on the weights. The weights would define the filter. And we can write the operation as a summation. Now let's generalize this even more with an integral. If integrals scare you, don't worry, because we'll return to summations when working with images since they are discrete. Notice that we can do a change of variables, say with a new variable called m prime, to replace m, and this results in the exact same form. What this means is it doesn't matter which function we consider the signal and which function we consider the filter. So now here is what we consider the definition of convolution. We usually represent it by an asterisk. We can do it for a continuous independent variable or a discrete independent variable. You can think of it as we are sliding the filter across the signal by changing the value of tau or m. Again, I want to emphasize that it doesn't matter if we slide the filter across the signal or if we slide the signal across the filter, since they would give the same result. One important filter is the delta function. In continuous time, it's defined as the derivative of the step function. The step function is just 1 when t is greater than 0 and 0 if t is less than 0. There is a discontinuity at t equals 0, and so there's a slope of infinity at that point. Since the delta function is the derivative of the step function, the integral of the delta function for any t greater than 0 is just 1. In discrete time, the delta function just has a value of 1 at 0 and 0 otherwise. Another name for the delta function is the impulse. And the impulse response is what we get when we take the convolution between the filter and the impulse function. Notice that if we convolve x with the impulse, we just get x back. So if we wanted to know what is the functional form of a filter or system or kernel, we could just pass in an impulse as the signal, and the result of the convolution would just be the filter. There are some very practical applications of this signal processing technique. One of my favorite examples is that we can build artificial organs. Remember that the organ's function is to regulate certain parameters in your body. So to replace an organ, we would need to build a machine that could exactly match the response of that organ. In other words, for all the input parameters like blood glucose level, we would need to output the same parameters that the organ does, like how much insulin to produce. So for every input X, we need to output an accurate Y. In fact, this sounds a lot like machine learning, doesn't it? Since we'll be working with images, we need to talk about two-dimensional convolution, since images are two-dimensional signals. You can see from this formula that this just does both convolutions independently in each direction. I've got some pseudocode here to demonstrate how you might write this in code, but notice that there is a problem if I is greater than n or j is greater than m. Well, we'll go out of bounds. What this tells us is that the shape of y is actually bigger than x. Sometimes we just ignore these extra parts and consider y to be the same size as x. You'll see when we do this in Theano and TensorFlow how we can control the method in which the size of the output is determined.